Dear students, we are starting with the second class of asynchronous counter, and in this class we would require the conversion of decimal to binary, right? The easiest way of conversion from decimal to binary. Suppose 10 is given and you want to get the binary of 10, then 10 is in what? 10 is in decimal, you want to get the binary. So how would you do? The conventional method is this: you are dividing 10 by 2, so 2 10 divided by 2, this is the quotient, that is 5, and the remainder is 0, right? And you go on, if you divide it again by 2, so the quotient becomes 2 and remainder is 1. So in this way you are getting this, fine, 1 0 1 0. So what is the binary of this 10? The binary of this 10 is 1 0 1 0, okay, right? So the easy way, this is a conventional method. The easy way is what? 8 4 2 1, right? 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. 8 4 2 1. So if you want to get 10, the binary of 10, then 8 plus 2 is equal to 10. So you put 1 here and 1 here, you get the answer, right? So suppose you want to get the binary of 15, then 8 4 2 1, 8 plus 4 12, 12 14 15. So the binary of 15 is 1 1 1 1. Similarly, if you want to get the binary of 35, then 1 2 4 8, it won't be sufficient, so we go for 16 and also 32, right? We will increase unless this number is gets greater than this number, right? So this is 32 is less than this. The next one would be 64, which would be greater than this. So we will stop here. 32 16 8 4 2 1. We want to get 35, right? So 32 plus 2 plus 1 is 35. So 35's binary is this. Similarly, if you want to get 60's binary, this would be 60's binary. Let's try this 26. We want to get the binary of 26, right? So 1 2 4 8 16, 32 won't be necessary here because this is 26. So 16 plus 8, how much is it? 16 plus 8, 16 17 18 19 20 21 22 23 24 25, right? So 16 plus 8 is 25 plus 1 is 26, right? So get the binary instantly, fine. Now let's go to our topic. Our topic was asynchronous counter, and what we have done, we have learned about asynchronous counters in with the help of what? T-type flip-flops. So what we have seen, one T-type flip-flop gives us mod 2 counter, and in the counting sequence what we get? 0 and 1, because if you can recall, it was only one flip-flop and either it was 0 or it was 1, and the sequence was repeating, right? 0 to 1, then again 0, then again 1. In this way it was repeating. Now if we cascade two flip-flops, right, what we have seen, we had got mod 4 counter. In case of mod 4 counter, there were 4 sequences: 0 1 2 3. For the first state was 0 0, the next state was 0 1, then it was 1 0, and then it was 1 1, and then it was 0 0 again. So if you decode these numbers, you get what? 0 1 2 3, right? And again 0, and it was repeating, right? Counters are like that. They will repeat a particular sequence again and again. Now with 3 flip-flops cascaded, we had mod 8 counter, and in mod 8 it was 0 to 7 and return to 0 again. In case of 4 flip-flops, we had mod 16 counter that you have designed, right? That was an assignment to design mod 16 counter, and you have successfully designed it. and it started with 0, went to 15 and returned to 0 again. So if you learn from the pattern, what you are getting is that whatever may be the count, say the n is the count, then it will count n minus up to n minus 1. From 0 to n minus 1 it is going to count, right? So if the counter is 10, then it will count from 0 to 9, and then again it will become 0. So this is the pattern, right? Whatever may be the number n, from 0 to n minus 1 it will count and it will return to 0 again, right? In case of mod 10 it will count up to 9 and then come back to 0 again. In case of mod say 12, it will count up to 11 and after 11 it will come back to 0 again, right? So let's learn drawing these break sequence counters, because until now we know how to design mod 2 counter, mod 4 counter, mod 8 counter, or mod 16 counter, right? So in this way, if you take 5 flip-flops, you will get mod 32 counter. If we take 6 flip-flops, we will get 64 counter. So in this way it will go on. But what will happen if we require a counter in between 8 and 16, in between 16 and 32, in between 32 and 64? So the objective of today's class is to learn how to design these counters which does not come under the category of 2 to the power n, because all of them are 2 to the power n counters, right? Because they can be explained by 2 to the power n. But we want to design today something that cannot be explained by 2 to the power n. So these counters are known as break sequence counter, right? So these counters are famous as break sequence counter. Okay, so suppose we want to design mod say we want to design mod 5, right? Let's start with an easier one. So mod 5 we want to design. Now what we would do, 2 to the power n should be greater than 5, right? So what would be the value of n? If we want that 2 to the power n should be greater than 5, then what would be the value of n? The value of n would be 3, isn't it? Right? So 2 to the power 3 is 8, so 8 is greater than 5, right? So this is the number of flip-flops. This is the number of flip-flops, right? So we must take these many flip-flops. 3 flip-flops we need to take, right? This is the first one, this is the second one, and this is the third one, right? So this is J0, K0, this is J1, K1, and this is J2, K2, right? So these are the clocks that we are giving, clocks, right? This is the first clock. Now if you can recollect, these are all what? T-type flip-flops, right? These are all T-type flip-flops, and the output of one flip-flop will give the clock of the second or cascaded flip-flop, right? Right, so this is what we are doing here. Q0, this should be Q1. Okay, understood? Fine. Now this is Q2. Fine. Okay. Now you will tell that, sir, what you have done? You have drawn only a mod 8 counter, right? But we require mod 5, right? Now what we need to do, we need to understand the sequence of mod 5, right? A few minutes earlier what we have discussed, if this is a mod n counter, then it will count from 0 to n minus 1 and then it will return to 0 again, right? So in case of mod 5 counter, it will count from 0 to 4, right? It will count from 0 to 4 and it will return to 0 again, right? So there must be some means so that whenever this 5 comes, the flip-flops gets reset, right? Because after 0 it will come 1, then 2, then 3, then 4, and after this 4 it should be 0, right? So whenever 5 comes, it should be 0, 4, then 0, right? So you should be able to decode this 5 state, right? So in case of 5, if you can recollect the counting sequence, in case of whenever the 5 comes, this would be 1, this would be 0, and this would be 1, isn't it? Q0, Q1, Q2, right? They would be 1, 0, 1, right? In case of 5, they would be 1, 0, 1. So what we are doing here, we are taking this 1 and we are taking this 1 also. We are taking only the 1s. We are not taking the zeros, right? We are only taking 1s and putting up a NAND gate here, right? So if these two becomes 1, 1, then the output of the NAND gate would be 0, right? Now if you can recollect, there are clear buttons here, right? What was the logic of clear button? If clear becomes 0, then all the flip-flops will become, output becomes 0. That is Q0, Q1, Q2 will be 0. If clear becomes 0, then Q0 becomes 0. If clear becomes 0, then Q1 becomes 0. If clear becomes 0, then Q2 becomes 0. So what we are doing here, we are connecting the output of NAND gate to these clear pulses, right? We are collecting the output of these NAND gates to these clear pulses, right? And once we do that, what would happen? That whenever 5 comes, 5 counting sequence comes, that is 101 comes, then these two ones will make the output of NAND gate 0, and this 0 is going to clear all the 3 flip-flops, right? Fine, okay. I think you have understood. So let us draw quickly. Let us draw mod 12 counter, right? Because now we can draw any counter we want, right? Any number counter. So mod 12 counter. So in case of mod 12 counter, first we need to ascertain how many flip-flops we would require, right? Mod 12, I'm sorry, mod 12. So we will require 4, isn't it? We will require 4 because 2 to the power 4 is 16, it is greater than 12. So we will require 4. So let us draw 4 flip-flops, 4 flip-flops, 4 flip-flops, J0, K0, Q0, J1, K1, Q1, J2, K2, Q2, and J3, K3, Q3, right? Right, so these are the clocks of the flip-flops. These are the clocks of the flip-flops, isn't it? Okay. Then all of them are T-type flip-flops. T-type flip-flops. T-type flip-flops. They should be short circuited and connected to plus VCC, right? So these are T-type flip-flops. Okay then. Okay then. Fine. Now the outputs should be connected to the next clock, right? So you would say that, sir, this is a mod 16 counter. No, we can make it mod 12. How? We only need to know what is the binary of 12. That is why we started with the conversion of decimal to binary, right? What is the binary of 12? 8421. 8 plus 4 is equal to 12, right? So 1100. So which ones will be 1 1? This will be 1 and this will be 1. So whenever this 12 counting sequence comes, then this Q3 and Q2 will be 1 1. So what we are doing here, we are taking Q3 and Q2, we are connecting one NAND gate, and the output of NAND gates we shall give in the clear pulses, right? Clear pulses of the counter. So the output of NAND gates are given to the clear pulses, right? We are giving to the clear pulses, so that whenever this 12 sequence comes, these flip-flops will get 0, right? So let us summarize what is happening here, that when we start the clock in this flip-flop, then the first state will be 0 0 0 0, right? And the next state will be what? 0 0 0 1, then 0 0 1 0, then 0 0 1 1, then 0 1 0, and in this way up to 11 it will count, right? Up to 11 it will continue to produce counting sequence, just like a mod 16 counter that you have drawn. But when this 12 comes, the moment this 12 comes, at that very moment it will return to what? 0. The 12 state is not going to stay. The moment it comes, it will become 0. So what we can say, after 11 it is getting 0, right? So this is it. This is the mod 12 counter we have designed, and if we put all these boxes inside this and we write it here, this is mod 12. So how many outputs we are having? Q0, Q1, Q2, Q3. So we are having 4 outputs: Q0, Q1, Q2, Q3, right? So another interesting thing that we can make with this, right? So suppose we have a mod 60 counter, right? Obviously the mod 60 counter will be given a clock, right? And inside mod 60 counter, can you tell how many flip-flops are there inside mod 60 counter? Inside mod 60 counter, how many flip-flops are there? So this should be the formula, right? 60 should be lesser than 2 to the power n. So it should be 6, isn't it? 2 to the power 5 is 32, and then 64. So it should be 6. So 6 flip-flops should be there. And the outputs of those flip-flops are Q0, and then Q1, and then Q2, and then Q3, right? And then Q4, and then Q5, right? So these are the outputs of these flip-flops. Fine. Now what we are doing, we are giving these outputs to a 7-segment decoder, right? We have designed 7-segment decoder earlier. So for each clock it is going to produce a digit. Suppose when the first clock comes, it will be 0 0. Then for the second clock it will be 0 1. Then for the third clock it will be 1 0. In this way, for a mod 60 counter, up to how much we are going to get these digits? 59, isn't it? N minus 1 rule. So up to 59, from 0 to 59 it is going to count, right? So you are going to see 59 maximum, and after that it will again become what? 0 0, right? Okay. So now what we are doing, we are giving this to another mod 60 counter. To make it more interesting, we are giving this as input to another mod 60 counter. So this Q5 we are giving as clock to the next flip-flop, right? So if you can recollect the principle of the flip-flop, right? So for a mod 4 flip-flop, if you give 4 clock pulses, the last flip-flop will receive 1 pulse, right? In a mod 16 counter that you have developed, what you have seen, if you give 16 clock pulses, the last flip-flop gives only 1 pulse. That is why it is mod 16, right? So in this case it is a mod 60 counter. So if you give 60 clock pulses, this Q5 will give only one pulse, the last one, Q0, Q1, Q2, Q3, Q4, Q5. This Q5 will give only one pulse. So for 60 pulses, you are getting one pulse here. Now these will also produce output, right, from Q0 to Q5, and to collect this we are having again another 7 segment display, right. So now this display, this being mod 60 counter, what is the maximum number that will come here? 59 again, right. So suppose these clock pulses are given 1 second, right, 1 second. The duration of these clock pulses are 1 second. So if the duration of the clock pulses is 1 second, then these digits will give you what? The second count, isn't it? 1 second, 2 second, 3 second. In this way up to 59 second it will go. Now once this 59 second is over, on the 60th second this pulse will go. So this is the minute pulse. So this is the what? This is the 1 minute pulse. This is the second pulse. This is the minute pulse, right? And when this becomes 60 minute, then in 60 minute what do we have? We have 1 hour. So now the counter will be mod 24. Why? Because 24 is 24 hours we have, isn't it? And in this way you can get the day, you can get the month, you can get the year. What is it? This is nothing but the digital clock. So with the help of this counter you can make the digital clock. Now can you tell me how you can get a pulse of 1 second, how you can generate a clock of 1 second duration? Because if you can generate a clock of 1 second duration, then the rest you know, right? So the question remains how you can develop a circuit which can generate a clock of 1 second, then you can make this digital clock, isn't it? Fine. Okay. Thank you all.